we're going to have two plates separated by D, and we're going to assume the area of these plates is enormous, really. It's huge, such that the square root of the area is much, much, much greater than D. Now, remember, area is really length times width, however you want to put it. And if you take that, if you made the length the same as the width, it would be like L squared, would be the area, the square root of that would be L. In other words, this dimension or this dimension, as far as the plate goes, is much, much greater than D. Right. So it's like almost two infinite planes. In here, we're going to have a dielectric, a value epsilon. And I'm going to make this the z-axis and make that 0. Therefore, this would be D. And now I'm going to solve the del squared of V equation equals 0. And really, I'm going to get the capacitance per unit area in a second. But what I'm going to do is this. I'm going to go ahead and put a plus voltage here, plus the minus. This is going to be V naught. And this down here, this lower plate, I'll just ground at 0 volts. Okay? With me? Now, what happens is, this is one way to do it. Actually, there's two ways to do it. A lot of times you assume charge. So, for this case, I'm going to assume a V, actually a voltage difference, V naught. Then I'm going to get the E field. Now, E field is equal to minus the gradient of V. You all agree with that? All right, when I look at this, this is equal to minus the quantity dV dx AX plus dV dy AY plus dV dz AZ. Are you with me on this one? Now here's where you have to have a little insight. When I look at this equation right here, if we assume that A is very large, matter of fact, have A, the area, tending towards infinity for now, then really there is going to be no change. If I come up a given height here, given Z, if I move this way, there is no change in the voltage with respect to either X or Y. Does that make sense to everybody? So these two derivatives can go away right here. So I'm left with E is equal to minus the divergence, or really minus the derivative with respect to Z, AZ. And here's the next thing I'm going to do. This one is a little, it stretches your confidence in the simplicity of some of this stuff. When I look at this, I look at something that has an infinite extent in the horizontal plane as far as there are two parallel plates. The only change in voltage which is going up, right? And really, I'm going to make this stipulation that the change from here to here, when I go V naught, I go from V naught to 0. When I take the delta V over delta Z, if I start from here to here, I'm going to get simply V naught divided by D. Does that make sense to everybody? Well, that, in effect, will be the actual value of the differential with respect to V, the derivative of V with respect to Z at any point in here, because the thing I'm going to make a case about, there is no change at any parameter that would change the rate that the actual voltage changes. In other words, the rate that it increases from this point to this point is a constant. Does that make sense? So that means I can say that this is actually equal to minus the change in voltage, which would be minus V naught over D AZ. And that's the E field. Now, when I take a look at the del squared, just realize I wanted to get to that E field because this is the important point. So when I look at del squared, well, let me do it this way, del squared of V, if you look in your books, this is a Cartesian coordinates. It's the second derivative V with respect to x squared, plus the second derivative V with respect to y squared, plus the second derivative V with respect to z squared, all equals 0, but this is between the plates. Between plates. All right, and I'm going to make make the case that this derivative and this derivative you don't care about because it does not vary with x or y, because the extent of the area of the top and bottom plate. Make sense to everybody? Only dv dz matters, right? The rate of change with respect to z. Now I go down and I solve this. Second derivative of v with respect to z squared equals 0. I think you remember how to do this. We integrate both sides, right, with respect to dz. And here, therefore, I'm going to get derivative of v with respect to z is equal to some constant. I'll just call it c1. You all know what I'm doing. If you integrate like dy dt, I say you have dy dt equals 0, you integrate once, you get y as a constant, right? Same here. So this first derivative is a constant. Then I integrate this again with respect to dz, and I get v of z is equal to some constant c1 times z plus c2. Realize it's very simple. I just integrated the second derivative of v with respect to z squared twice, and I get the voltage with respect to z is some constant c1 times z plus c2. Do you all agree with that? Now here's how I figure out what goes on. I could do it just with that. I showed you this because this is a way, it gives a lot of insight into getting the value of E, and from E you can easily get, just from that divergence equation over there, you can actually, from minus grad V equals E, you can solve for V. But now, right here, I'm going to do this. Different marker. This one's got it. Well, what do we know? We know that V at 0 equals 0 volts, right? When Z is 0, correct, class? And that means C1 times 0 plus C2 is equal to 0. And what does that really tell us? C2 is 0. That's right, C2 is 0. So now we have V at D is equals D is equal to C1 times D plus 0, or really good. Or we can say that C1 is just what? If this is equal to V naught, right? V of D is V naught, am I drawing? Well, that's equal to C1 times D, and D is D's given, so C1 is V naught over D, and that means your equation V of Z is C1 V naught over D, and that's it, times Z, right? There is no C2, correct, class? All right, now, if you look at that, what is the E field? Well, the E field, by definition, is equal to minus the gradient of V, right? Right over there. Agree, class? Well, what is that? This only varies with Z, right? When I take a gradient, it's going to be minus dV dz az, or you can see it's simply going to be minus V naught over D is equal to az is equal to the E field. And that's how you get the electric field. We could get the capacitance too, we'll do that in 1 second per meter. That's how you get the electric field from the voltage, some differential voltage, and this is how you go about a solution of, it's called, this is actually called the Laplace equation when rho v equals 0, of the del squared V equals 0. You go through it and you get this. Now, the real truth is, the way we're usually after something called capacitance. Has everybody heard of capacitance here? Capacitance is something in your circuits courses, you always looked at it as two parallel lines with a separation distance. And capacitance, they gave you some equations that talked about how it can be used to determine current flow. Where in steady state, it was C dV dt was equal to I, and at a constant frequency, you were given capacitive reactance, was the ratio of voltage to current. It was 1 over j omega c. Those don't really tell you about what capacitance means, but this is the fundamental definition. When you have capacitance, if you have any two plates, matter of fact, let me do this. I'm going to say there's a plate 1 and some plate 2. And you apply a voltage to this, it will induce a plus charge here and an equal and opposite minus charge here if there is a voltage applied here, plus or minus V naught. right? Now, capacitance is by definition. Capacitance is equal to charge divided by voltage. The amount of charge, magnitude of the charge on either one of these plates, divided by the voltage developed between them. That's the definition. Most of the time you see it written like this. The Q is equal to C times V. There's always two plates involved. It's always a plus to minus voltage relationship, and this charge will, or it's really a plus to minus charge. Whatever charge is induced here, the opposite charge is induced in this one. And that's just the reality. Now, what does capacitance really do for us? It tells us something about the ability of these two plates to store energy. And it gives us a ratio of charge to actual energy. Write this down. The energy stored in a capacitor, and I'll just call it WE, and this is in joules, is equal to 1/2 times the charge times the voltage, and it's equal to 1/2, CV squared, pardon me. It's charge times voltage squared, and I think you've seen this before. Let me actually do it this way. 1/2 CV squared, that's the energy in a capacitor. It's electrostatic energy, and this energy can be recouped. So if you charge up a capacitor to a value V, you have this much energy, 1/2 CV squared in it. Now, if you put a resistor across it, a resistor across the capacitor, once it's charged, you can get all that energy back out. Understand? It's stored. It's not launched electromagnetic energy, it's stored. You could write this as, since Q is equal to CV, you could write it as 1/2, and then C would be Q over V times V squared, or 1/2 Q times V. That's another way to think about it. And then since V is equal to Q over C, you could also write this as 1/2 Q, and V is equal to Q over C, or Q squared over V. All these are the same thing, essentially. This is the most common form. 1/2 CV squared is usually the way you think about energy in a capacitor. Have you all seen this before in physics class? Now, I'll tell you about capacitance and energy. When I was working, we did a railgun project over here. It was a senior design. We built one. And we needed to store a lot of energy in these large capacitors, and we had to get it out very quickly. And we had about 10,000 volts. We could charge them to about 10,000 volts. And these were a total of 33 millifarad. Now, that is an enormous amount of capacitance that can have a breakdown of 10,000 volts. All right? That is an enormous amount. So the energy we had was 1/2 times C, 33 times 10 to the minus third, times 10,000 squared, or 10 to the 8th. And we had an enormous amount of joules in the sense that something was readily available. And when we discharged that into the railgun, we created a current of up to 400 kiloamps just for an instant. That's an enormous amount of current, and the magnetic field was phenomenal. But the thing that always caught me was, our discharge time was maybe less than a millisecond. So we've got, let's see, we have 33, call it 1/3 times 10 to the minus second times 10 to the 8th. So 1/3 times 10 to the 6th times 1/2, so 1/6 times 10 to the 6 joules that we discharged in 10 to the minus 3 seconds, or we had a power of about 10 to the 9th, it's just shy of 10 to the 9th watts, which is an enormous amount of power. Just think about it. Hair dries, what, 1,000 watts, 500 watts, something like that? 10 to the 9th watts of power. And we launched, when we discharged this thing, it was caused I know it launched a propagating wave, but the thing that amazed me was when we did that, the magnetic field was so large that the wires that were carrying the current, remember, I don't know if you remember this from physics, current in the same direction pull together, current in opposite directions repel, all right? Well, when we launched that, we had to have an inductor in it to slow the discharge. We had this large inductor that really had a core that was we had PVC piping there, and we wrapped this 4/0 wire, and we had to put layers of, it was really fiberglass. If you've ever done any work on a car, you use this Bondo stuff, fiberglass on there, put layers and layers of that to hold it there. And we could take a can, an empty can, and put it in the center of that thing, and it would launch it into the ceiling like a rocket, and would also crush it at the same time. And the wires would jump, sometimes sparks would fly. If you had a corner outlet like that, you would see sparks fly from there to the ground. It was a really an enlightening time. I realized just what level of energy and power we were dealing with. And we were inducing currents and everything. And we were causing all sorts of trouble. I'm surprised the computers didn't fail. But I'm giving you that is an idea of how capacitance, that understanding the energy in that capacitor and how fast it discharged gave me a pretty good idea of the level of, you might say, disruption in the environment. If you're only talking about 1,000 watts as your peak power, that's not much. You're talking about 10 to the 6 watts, things are gonna get a little uncomfortable. You're gonna hear clicks and stuff like this in your system. 10 to the 9th watts, all holds barred. You don't know what's going to happen. Right? And that's, but the way I got it is I knew how much energy was in there, I knew our discharge time. So, and capacitive electrostatic energy. All right, that's the first thing. Second thing we're going to talk about is a cylindrical, well actually I'm going to do a spherical one next, and then I'll do cylindrical last. But I didn't even get the capacitance for this one, so we're going to right now. This is something I'm going to cover later today, but we had the electric field between the plates given as simply equal to minus V naught over D AZ. Do y'all agree with that? Now, something we're going to see later on is if you have a perfect conductor, this is a perfect conductor, which means sigma is tending to infinity, and it interfaces with any dielectric, D normal on this will be equal to rho S, and furthermore, E normal will be equal to rho S over epsilon in the region. Now, that's an important fact because we have E normal, right? Isn't this the normal component to that? So keep watching this. Now, D normal is rho S, E normal is rho S over epsilon. So I can say that minus V naught over D, that's E normal, divided by epsilon here, would be equal to rho S. Do y'all follow me on this? So that would be rho S, and this would be on the top plate. Now, on the bottom plate, if y'all see this, you see how the electric field is pointing into this? And it's coming out of this, right? That means there's positive charge here, negative charge here. The electric field lines terminate on negative charge. Does that make sense to everybody? So that's the charge density in the top plate. Well, if I look at this, this is, rho S is really charge per unit area, isn't it, class? Correct? So therefore, the capacitance per unit area would be the charge per unit area, right? If you look at that, divided by the voltage creating it. Well, the charge per unit area is rho S over the voltage creating it, or it's what? Think of this as a magnitude of charge, by the way. Capacitance is always positive. So when I look at this, it would be V naught over D epsilon, right? Divided by V naught, or it's simply 1 over D epsilon really is going to be the value of the capacitance per unit area. And that's for a parallel plate capacitor. So just try to understand this. The capacitance is inversely proportional to the distance between the plates and epsilon. Now that's per unit area, right? Class? And I've assumed that these plates are massive in their extent. And y'all know that when you're talking about capacitor, if you looked at the reference, really the scale, the area of the two plates is much, much larger. The distances involved in the perimeter, I should say, of the plates that actually are containing the charge that is, for any reasonable capacitor, is much, much greater than the separation distance. As a matter of fact, I think maybe I did tell you this. You can make a fairly decent, an interesting capacitor. Did I tell you about the aluminum foil in here again?
Yeah,
I did. Well, if you just take aluminum foil, sheets of aluminum foil, and put wax paper and then aluminum foil on top of it, you've got a capacitor. Now, if you think about the separation distance, that wax paper is very small. I mean, it's, I don't know what, maybe 30 microns or so, 40, 50 microns, something like that. But the aluminum foil, it can have a feet, or 1 or 2 feet in width, right? And it's as long as you want. That's sort of like the relative dimensions of capacitors in general. Separation distance is extremely small compared to either dimension of the plate, if they're rectangular. Now, if we wanted the capacitance of something that was a parallel plate capacitor, where the area of the plate, square root of the area, is much greater than the separation distance, that's equal to epsilon A over D. And that is if the dielectric epsilon is a constant. Do you all remember that? Capacitance for parallel plates is always proportional to area, inversely proportional to the distance. And epsilon there gauges how much more it can store, more energy it can store than free space. Free space would be epsilon naught, right? But if you had a material with an epsilon relative of 50, it could store 50 times as much energy as free space could for the same geometry and same voltage. And that's important. So it increases the energy storage ability. The next one we're going to do is going to be, I'm going to do spherical next, because this is the one that, it's a personal favorite of mine. Now, spherical capacitors, I'm going to say this, they have one unique fact. There is no real inductance associated with a spherical capacitor, which means theoretically they can discharge at a rate only limited by the inductance of the wires external to it, which is phenomenally fast. Have you heard of supercapacitors in here? Anybody? Well, you can get these. My friend Dr. Birch over in mechanical engineering told me about what he did. A supercapacitor is something that can store a whopping amount of charge, but a very low voltage breakdown. All right, so that's the trade-off. If you want a larger voltage, you have to have much less capacitance or for a given region of space, or it'll break down. So he bought one of these supercapacitors, and he could take that, and if you discharged it like into a nail or something, it would melt it. Because it could store so much charge, but it was an extremely low voltage. Follow me on this? And that means it's extremely small dielectric, thin dielectric. Well, I'm not going to get into how they're made, but that's something that stores a lot of charge. A lot of times you're not worried just about that, it's how fast you can get the charge out. And what I'm about to show you is a spherical capacitor, and this has virtually no internal inductance. We'll see that later when we cover inductance. So for a spherical system, spherical capacitor, what we do is we put an inner radius A, and then we put an outer radius B, and we do this. We're going to assume that this inner thing is solid metal. It could be just metallized, and we're going to metallize the outer surface too, or make it a good conductor. And then what we do is tunnel a hole. We're going to cause a small little hole to come through here in the dielectric. Remember, this has got a dielectric epsilon between the plates. And we're going to run a wire right to this and connect it there. We'll put a voltage and ground the outer part. So you have a ball. Sorry, forgot to shut this thing off. So you have a ball like that, okay? Now, you also develop a plus charge on the inner conductor and a minus charge on the outer conductor because it is a capacitor. And we're going to solve this problem. And the way you do this, I'm going to just say this because right now I'm solving the Laplace equation, but I'm doing it with the intent of also extracting the value of capacitance. I'm trying to kill two birds with one stone, because that's what it's really used for. So usually when you're trying to solve the capacitance for any system, you either assume voltage or assume charge. The last one I assumed the voltage for the planar case. And to be frank about it, it's better to assume voltage for that. For this one, I'm going to assume a charge. And the way it works is this. You assume charge, and the next quantity you get is the D field, irrespective of geometries. R is a spherical geometry, right? And we know we can use Gauss's law, and we know the integral of d dot ds over any closed surface is equal to the charge enclosed, Q inside that surface, right? Well, now I put up my Gaussian surface at some region R, and R is between A and B, and I put my little Gaussian surface there, and I'm going to make the case that the D field's always in the radial direction. Can you all accept that, class? D's always radially outward in a spherically symmetric system if this thing's centered at the origin. Y'all give me that? And if that's the case, then I can go ahead and say, give me 1 second. I can say that this boils down to D, really in the radial direction, times 4 pi r squared is equal to Q. I'm just going to call it Q. And that means that D of R is equal to Q over 4 pi r squared AR. You all accept that? Right? Because it's like a point charge, really. If you're outside where the charge exists and it's spherically symmetric, you just take all the charge inside there and divide by the surface area. Now, you'll notice this has nothing to do with any dielectric constant, right? The next step is important, so I get D. After D, you get the E field, and the E field is going to be equal to simply D over epsilon, or it's equal to Q over 4 pi r squared epsilon AR. Right? I'm doing this two ways. This is the way Spokey does it this way. I'm going to do it another way in a second. So now I have E. Now remember, the capacitance is equal to charge over voltage, right? I assume capacitance, I'm after voltage. What's the next step to get the voltage? You see it, I'm sure. We got E. How do you get voltage? Gradient. Well, E is equal to minus the gradient of the voltage, or we could say the voltage is what? Equal to minus the integral, right? From the inner to the outer, or from the outer to the inner. In this case, from B to A of E dot dl. I'm going to I want to make sure you understand what the capacitance is strictly positive. So if you get a negative sign in front of this thing, in terms of it's got a negative quantity, just take the magnitude. All right, what is this going to be? That's equal to minus the integral from B to A of the E field, which is this, of Q over 4 pi epsilon r squared AR dot dr AR. And I didn't put the rest of the differential because DL is just dr AR. I don't need to put R sine theta d phi a phi and R d theta a theta, because the dot product of AR with them is 0. So I only put this term. Now when I do this integration, I'll do it up here. I found out that the voltage between the plates, you can call them A to B, is actually equal to what? Q over 4 pi epsilon, and then integrate 1 over r squared. What do you get? Minus 1 over r, right? But there's a minus sign, so it's plus 1 over r, and then it's going to be 1 over A minus 1 over B. Now here I have to caution you about one thing. You see, I assumed this value of epsilon right here was a constant, right? It doesn't have to be a constant. it could be epsilon naught over r. And in that case, then this epsilon naught over r times r squared would be epsilon naught r down here. With me on this? And the integration would not end up as this. So this, what I'm showing you, is only true if epsilon is a constant. And then, if I have the voltage, how do I get the capacitance? Q over V, right? I assume Q, and I've got V, so what happens? When I take Q divided by V, I get what? 4 pi epsilon over 1 over A minus 1 over B. And that's the capacitance between the inner and outer shell for a spherical capacitor. Make sense? We're going to do the same thing, only this time I'm going to use the voltage equation. I'm going to assume voltage. This is with charge. And I'm going to use the Poisson equation. So here we start with del squared V equals 0, and that's between the plates only, between plates. Now, this is in spherical coordinates. If you look at the back of your book, you're going to see that this becomes 1 over r squared ddr of r squared times the vdr, plus, and then there's two other terms. You guys, you have your book, right? You have your book? No. Yeah. If you look at your book in the back page, or the back cover, pardon me, I'm just going to show you. Mind if I do this? And back here, it shows Laplacians, the last thing in spherical coordinates, and they have derivatives with the next set of derivatives with respect to theta and with respect to phi. If you look in the back cover, the only one I care about is the derivative of v with respect to r, and here's why. Because if I'm at a certain range, a certain value r away, if I change either theta or phi, the voltage does not change. It's constant for a constant distance. So therefore, you don't have to take the other two parts of that Laplacian operation. And we say this is equal to 0. Now, follow me on this one. I think people can easily mess this one up. You all see if we multiply both sides by r squared, it goes away? You agree with me? So now I have this, I integrate one time. I have ddr of that. Well, when you integrate once, you get a constant. So then I have r squared times dvdr, right, is equal to c1. Do y'all agree with me there? Right? Now I divide c1 by r squared, and I get dvdr is equal to c1 over r squared. And then I do another integration, follow me? When I do the next integral, I get v of r is equal to minus c1 over r plus c2. Agree? Now that's the equation for voltage anywhere between the inner radius and the outer radius, between A and B. Now you can do it this way. I calculated the voltage difference after I assumed charge. Now we're going to calculate charge. So we're going to, based on the assumption of voltage. So I assume a voltage, or I assume that V at R equal A, the inner radius, is equal to V naught. All right? Give me that, everyone? The next thing I'm going to do, if that's V naught at R equals A, now I write this equation down and I say that V naught is equal to minus C1 over A plus C2. That's the first condition, right? What's the second condition? Boundary condition. Boundary, it's a boundary. Where's the other radius? B, and what's the value of voltage? 0. So now I can say that 0 is equal to minus C1 over, this is C1, C1 over B plus C2. And here you can see that C2 is really minus C1, or I should say C2 is equal to C1B, right? C1 over B. You agree with me? Now I can go ahead and I can say that based on that, this equation right here becomes V naught is equal to minus C1 over A, and C2 is plus C1 over B, or simply that C1 times 1 over B minus 1 over A is equal to V naught, or C1 is equal to really V naught divided by 1 over B minus 1 over A. Do y'all agree with me there, class? Now I go ahead and I'm going to do it right over here. And I take that and I say that now my V naught, or sorry, V of Z is equal to C1 minus C1 over R. So it's equal to minus V naught over 1 over A minus 1 over B divided by 1 over R. That's an R right there. Plus C2, and since C2 is C1 over B, this becomes V naught over, and since it's divided by B, I have B times 1 over B minus 1 over A. And that's V of Z. Do you all agree with that? I know the constants are a little odd right there, but we can simplify them if we want. I can say one other thing. Well, I'm going to leave it like that. Are you with me on this one? Now remember, what I'm after is I assume voltage, I'm after charge, right? And here's how I'm going to get it. When I get the D field, listen, when I get the D field, I know the D field normal, right at that surface, is going to be the charge density. And I can take the charge density and integrate it over the surface area, in this case just multiply it by the surface area, and get the charge on that plate. Do you all agree with me there? So now I need the D field. Well, to get the D field, I need the E field, right? What is E? In terms of V? Minus the gradient of V, right? This is spherical coordinates. If you look at the gradient operator in spherical coordinates, you get this being equal to minus dV dr AR. There's two other terms, but the derivatives are equal to 0 because they're with respect to angle, theta and phi. The derivative voltage with respect to either of those angles is 0. That means this is equal to minus the derivative of this. Well, what is the derivative of this? Right here. Derivative of this is what? 0. Derivative of this with respect to R would be what? Minus that quantity over 1 over R squared, or it becomes simply V naught over 1 over A minus 1 over B, right? Divided by 1 over R squared. Do y'all see what I've done there? And that's in the AR direction, by the way. Gradient operator is a vector. So that's the E field. If I got the E field, how do I get the D field, people?
By epsilon.
Yeah, D is equal, well, E is equal to D divided by epsilon, right? I'm sorry, D is equal to epsilon E, so if I want E, I divide that by epsilon, you're right. So now I can say that the D field would be equal to V naught divided by 1 over A minus 1 over B, and then it's divided by epsilon R squared AR, and that's D vector. That's also the normal. So now the next thing I get is the charge density at R equal to A. You can do the other one too. That means rho S, charge density at R equal A, is equal to V naught over 1 over A minus 1 over B, epsilon, and A squared, right? You agree with me, everyone? Yeah.
If E equals D over epsilon, why isn't epsilon multiplied?
Oh, I mean, sorry, that's my mistake. Thank you. You are absolutely right about that. Forgive me. Thinking about about something else right here. Right here, yeah, it should be multiplied by epsilon right there. My bad. You agree with me there? Now at that point, if that's rho s, to get the total charge on the inner surface, Q, that would be equal to, technically it's the integral of rho s over the surface area, right? But in this case, I can just take rho s times the surface area. So it would be V naught epsilon over 1 over A minus 1 over B times A squared. And what's the surface area of the inner sphere? You know? 4 pi, in this case, A squared, right? 4 pi A squared. And you can see that the A squared's canceled, right? So then, do it up here. I see that Q is equal to V naught epsilon over 1 over A minus 1 over B times 4 pi. And that's Q. Agree? Again, we didn't assume charge, get charge, get D, get E, and then get V. Here we assume V, then we got E, and then we got D, and then we got rho, and then we got Q. So now I have Q, and finally, what is the capacitance?
Q over V.
Q over V, and you can see in that case, I simply get rid of the V, and I have 4 pi epsilon over 1 over A minus 1 over B. And that would be it. Now the thing you have to guard against is assuming this is true if epsilon is a function of position. If epsilon is a function of position, it's not true. You have to do the integrate. Then when you get to this point here, well actually when you assume epsilon is a function, epsilon is a function of position, it's probably best to do it assuming charge and then D and then E, because we won't get entangled with, let me show you why I'm saying what I'm saying. Remember when we had divergence of D is equal to rho V, right? And then we said that, well, that's equal to the divergence of epsilon E, right? Right there. And that's equal to the divergence of epsilon times minus the gradient of V. Follow me? This would be the equation you'd have to solve to get the rho, if rho V, this would be the equation. You could still say rho V is 0, would be that one. If this was something that's a function of position, you would have to take the divergence of this, which means you get 2 terms there. So it's easier to assume charge, then get D, then get E, and then get V. I'm just leveling with you, that's the best way to do it. Anyway, that's the same thing. Now, I'm going to do one of these. This is as good a time as ever, where I'm going to make epsilon a function of position, and you'll see the difference. Matter of fact, I'll let you figure it out. I want you to try this problem. Find the capacitance between the inner A and outer conductor B. This is in spherical symmetry. If epsilon is equal to epsilon naught over R. I want the capacitance. And I'd assume that I would suggest you assume Q, get D, get E, and then get V. All right, let me go get some markers, because these are, honestly, these are just unacceptable.
I think I have some.
Now, I'm gonna get them I'm gonna get like 3 or 4 from over there. We're gonna assume a plus charge on the inner one. That means the outer one is grounded, right? Once I do that, I have the D field here equal to Q over what? Anywhere between, if I'm at a distance R, what's the D field? always, it's what? The integral of d dot ds is the charge enclosed, right? I assume charge, what's the surface area?
4 pi r squared.
Right, so this is 4 pi r squared, right?
Yeah.
AR. Now, if I have D, how do I get E?
Q over epsilon.
D over epsilon, right? So then I get E, and I say that the E field is simply D over epsilon, right? And that means it's Q over 4 pi epsilon r squared, right? AR. But what's epsilon? Q over 4 pi, what's epsilon? Right. Epsilon naught over r squared AR, right? What do you see happening there? What's the E field? R squared divided by R is R. So now I have the E field being given as Q over 4 pi epsilon naught R AR, right? All right, what's my next step? Well, how do I get V?
Integrate
Right, integrate this with respect to R, correct? So now I get V is equal to the integral of E dot dl. Technically, it's minus the integral of E dot dl from B to A, but I'm not worried about this because if it's a negative sign, I just take the magnitude. So here I get minus the integral of Q over 4 pi epsilon naught R AR dot dr AR from B to A. And what's that? That's actually Q over what? 4 pi epsilon naught. What's the integral of 1 over R?
natural log.
Natural log, right, of B over A, right? That's V, correct? And finally, what's C?
Charge over voltage.
Right, Q over V. We started with charge, right? We divide by voltage, you'll notice the charge cancels. And you get this being equal to 4 pi epsilon naught divided by natural log of B over A. Were you on that trail? Both of you guys? How many saw how to do this? Usually, I mean, this stuff's almost gotta be natural. Here's the problem, epsilon naught R, when you see that R squared, you've gotta have epsilon as, if it is a function of R, you put it there and you multiply. And you can see it, now it's just a function of R, 1 over R. Everybody got that? All right. Now we'll do cylindrical briefly. Now, whenever you're doing cylindrical symmetry stuff, it's usually, it's an infinite type of thing, so you have to basically limit the extent of the actual pipe you're talking about. But we're gonna assume that we have a long pipe with an inner radius A, so think about this. An inner radius A, an outer radius B, and in between these we have some epsilon. Remember, epsilon can be a function of position. We're just gonna make this thing a height h. We could let h be 1, but in this case, I'm just gonna arbitrarily say h. So then, if you look at this, basically the region between A and B has a dielectric epsilon. Now, watch what I'm saying. I'm gonna, tell you what, I'm gonna go ahead and make h1 because it'll make it easier. I'm gonna go ahead and I'm gonna place a total amount of charge on this inner conductor here of Q. So I put plus Q on there. Now you can see that that plus Q is distributed over 1 meter, right? And it's going to uniformly distribute itself over the inner surface. Understand, everyone? So then from Q per, really, this is going to be the rho L, isn't it? It's going to be the charge per unit length. Do you all agree with that? Because I made it 1 meter, so it's the charge over a meter or the charge per unit length. Do you agree with me? So that's rho L. And that means, well, we could use Gauss's law, but how many remember what the D field is for a line charge? Do you remember, isn't this like a line charge? It's charged by unit meter? Well, what is it? Well, the D field is always what? It's the charge divided by the surface area for a constant D field. Isn't that surface area just 2 pi times the radial distance rho times the height? Right, and I'm saying this is out at a distance rho here. So from here we get D, and D would be equal to this charge plus Q over 2 pi R, right? And we're making H just 1, and it would be in the AR direction. All right, that's the D field. What can't you see? You struggle.
What is that? It says Q equals.
Rho, that's rho L.
Okay.
I'm trying to do a script rho L, but that might be a little better.
Thank you.
All right, now, that's D field, right? Because Q is rho L, it's the charge per unit meter. I've assumed that. How do I get E? Class?
Yeah, over epsilon.
Divide by epsilon, right? Divide by epsilon. So then I get E is equal to D over epsilon, and it's Q over 2 pi epsilon R AR. This is the point, if epsilon is a function of position, you need to do the multiplying here. Follow me? And actually not R, but let me use rho, because he uses rho in his book for this. I personally don't like to use rho for anything with charge density, but he uses it as the length, the radial length in cylindrical coordinates. So now I have E. Finally, how do I get the voltage once I have E?
Integrate.
From where to where, you're right?
A to B.
All right, so now I can say the voltage between B to A or A to B is equal to minus the integral, and you don't need to worry about that minus sign, of from A to B of Q over 2 pi, that's 2 pi, epsilon, rho, A rho, and what's DL for this one? Class? It doesn't, I mean, this just need D rho, A rho, right? I don't need to put the rho, D phi stuff and all that, so it's just D rho, A rho. And you can see the A rho dot A rho is 1, so what is the integral of this? It's gonna be Q over 2 pi epsilon, and when you take that's actually E to A. When you take the integral of 1 over rho d rho, you get, what's the integral of 1 over x dx?
Natural log.
Natural log, right. So it's the natural log of b over a. Now, if you have a over b, it would be a negative value. Just take the magnitude, or invert it, and put b over a. And that's VBA, right? So then finally, how do I get the capacitance per unit meter, per unit length? Capacitance is?
Chargeable voltage.
Right, so I divide charge by this, you can see the Q's cancel. Charge by this, Q over 2 pi epsilon, natural log of B over A, or I get simply 2 pi epsilon over the natural log of B over A. That's the charge per unit length of a capacitance per unit length of a coaxial cable of inner radius A, outer radius B. But it is per unit length, remember that. Now, one thing to take note of, as the radial distances get close to each other, as B gets close to A, where's that logarithm going to? Log of 1. What is log 1? 0, right? What is 1 over 0? Infinity. So what I'm getting at, as that separation distance gets smaller and smaller, the capacitance per unit meter is heading to infinity. And this is the catch. As you lower that distance between B and A, you get a larger capacitance, but the amount of voltage it can hold before it breaks down goes way down. And that's always the trade-off. If you want a supercapacitor, it's usually good to make it 10 volts. Whenever they hear the term supercapacitor. Put more than 10 volts on it, it'll punch through the dielectric, and it's usually not self-healing, so your capacitor is doomed. But if you want something that can withstand a lot of voltage, like if you're going to use a capacitor for some sort of filtering at say 200 volts, 300 volts, then you want something with a fair amount of dielectric strength. You want something that won't break down, And that means a much larger capacitor for a given amount of charge handling ability. I use the word self-healing. Can you think of any capacitor that is self-healing? It means the dielectric will heal once it's broken down. There's one particular one. It's any dielectric that's made of oil. Now, there are both transformers that use oil as an insulation, and there are capacitors that they're oil filled. And the reason that is if they ever break down, they're healed though. They're not, unless they blow up. I mean, if there's a continual breakdown, a continual arc, it'll heat up and blow up. And if you've ever seen these transformers out there, I don't know if you've ever seen this, but transformers, on power lines, a lot of these things, they're gonna assume they're gonna have problems with, and Dr. Gross would know more than me. And some of them, they have dielectrics that are self-healing. If they break down, they'll repair themselves. Well, I think it's, they use a compressed NF3 gas in some of them. NF3 is nitrogen trifluoride, and they also use, I think it's SF6, silicon hexafluoride, because they have a large their breakdown strength is very large compared to air. But whenever they break down, you'll see these incredible blue and red glows. Have you ever seen a transformer blow up anyone? It's usually blue or real red. I don't know what color you saw. Do you remember? When you saw it and you've seen it?
They're blue.
The blue ones? But they're spectacular. It's an enormous like blue flash, and I think that's because of sulfur hex, or I'm sorry, I think it's sulfur hexafluoride, but I don't know that for a fact. Gross probably would. Okay. Now, next thing. I want to talk about energy density. I gave you the energy in a capacitor is 1/2 epsilon, 1/2 CV squared, right? But there's something called the energy density. It's like power density. Do you remember what the power density was in material? It was J dot E, right? Or it was equal to sigma times magnitude of E squared, or it was equal to what? J squared over sigma. And remember that E times sigma is equal to J, right? And J is the conductivity. Now this is a power density, and that's in watts per meter cubed. Energy density is like it. The symbol for energy density is WE. This is energy density. Well, that's equal to, now take note of this, this is 1/2, all right? And it's going to be D dot E. That's the technical definition. Or it's equal to 1/2 epsilon times magnitude of E squared, or it's equal to 1/2 magnitude of D squared over epsilon. And the units of this are energy or joules. Density means meter cubed. Now, I got to tell you one thing about this, so you know. This is the one I always use, right here. 1/2 epsilon E squared is the energy density. Do you know that from physics? Does anybody remember this from physics? Well, you know what energy is. It's in joules. Density is the amount per unit volume. That's all it is. So if you wanted to figure out what the value of a capacitance is in a region, normally I said assume Q, right? Then get D, correct? Well, at this point, you could just say from D, we could get the energy density, right? That would be 1/2 D squared over epsilon, right? And then once we had the energy density, we could simply get the total energy equal to the integral of the energy density over the volume, right? And that would be equal to 1/2 CV squared, and therefore, from assuming Q, D, maybe, actually, for this one, we can go, we can go 1/2, you're right. 1/2 Q squared over C. We could get C that way. Agree, class? Because we assume Q. Therefore, when we get the energy density, when we calculate that, we could study it equal to 1/2 Q C squared, and the Q's would cancel, and we could calculate C from there. That's another thing you can do, but keep in mind that energy density is very important because it's something that you're gonna find out, especially when you do modeling of things. Energy density can vary widely, and you would like to always know the total amount of energy in a system that can be extracted, so remember that. And I don't have time to go on too much longer with that. But there's no class Friday. I'm gonna give you some homework. Let's forego the quiz on Monday, and we'll look at one maybe Wednesday, okay? And we also have to vote on the test today, right?
Mm-hmm.
All right, now I've got everybody here, so we can. So do you have test dates in mind? Josh, you're very good. Do you have one in mind? Doesn't matter to me.
Next week. Friday of next week?
All right, that's fine with me. I'm gonna make one comment for everybody's sake. Usually, in my experience, Monday tests score the highest, Fridays are the worst. However, this is the summer, there can be exceptions. I'm saying that's usually the way it is. But if you want, let's see, we'll take it Friday, and what date is that? Let's see.
28th.
28th of June. Any other dates?
What the Wednesday after that?
All right, so then we got Monday, and then we got Wednesday, so this is July what?
3rd.
We don't have that day off, right? We have the 4th. All right, so this is July, this is the 3rd of July. Any other dates? You want that Monday too or not? You want to just vote on these two? All right, if you want it Friday the 28th, one hand up, one hand, hold it up. I count 3, right? All right. If you want July 3rd, one hand. I count 2, 4, 6, 7. All right. So it'll be July 3rd unless there's a disaster. I hope not.